Okay. So you may remember that on Friday, we were talking about failure. And this was in the context of drilling a hole in the ground, which is basically what you're going to be doing if you're doing geothermal drilling. You're drilling holes in the ground. And so we talked about two different types of failure. Remember, we talked about, let me go back to this more Coulomb diagram. If you're representing your state of stress with a Mohr circle over here, if you intersect your failure envelope at positive normal stress, that's going to cause shear failure. You'll get those conjugate fractures form. And if you intersect it at negative normal stresses, you'll get a tensile failure fracture. And so that's going to be where the walls of the fracture pull apart. And so there are different conditions under which those different modes of failure happen. And if you're thinking about drilling a well, the two things that can happen are if your pressure in the wellbore is too high, you're going to induce tensile failure. We call that a drilling-induced fracture. And that's a bad thing because you lose drilling fluid into the fracture, you lose your ability to control the pressure downhole, you lose your ability to carry the cut pieces of rock up through the hole. So that's overall a bad thing. If your wellbore pressure is too low, you can induce shear failure in the borehole wall. And that's a bad thing because then the borehole starts caving in on you. And again, you can lose control of the well, you can get your drill pipe stuck. This is not a good thing. So you want to define the conditions within which you can have a safe, range of pressures within the wellbore that you're not going to create tensile fractures or shear failure. And so we talked a whole bunch about the stresses around the well. We defined the local state of stress on the wellbore wall, where we have the radial stress and the tangential stress or the hoop stress. And we considered the different conditions under different situated circumstances of failure. So we said that for tensile failure, the minimum pressure to induce tensile failure is given by this equation. And we know that the fractures, if you form them, they'll form 90 degrees away from the minimum horizontal stress. This actually, just kind of as a side note, if you're a geomechanics person and you want to know what direction your maximum and minimum horizontal stresses are, you can look at boreholes that have been drilled in the area where you're looking and look for drilling-induced fractures. And you can say, okay, I know that the drilling-induced fracture is in the direction of the maximum horizontal stress. So the minimum horizontal stress is 90 degrees. So that's something you can actually do that's useful with these things. But that's going to be your tensile failure. Now, shear failure, on the other hand, the mathematical treatment of this was a little more complicated. We had to make the simplifying assumption that the horizontal stresses were equal to each other. But after a bunch of trigonometry, we came up with a critical minimum wellbore pressure below which you'll have shear failure. And that's given here in terms of the horizontal stress, the angle of internal friction of the rock, and then the cohesion and the pore pressure within the rock. And so our summary here is that we've got now some bounds on the maximum and minimum wellbore pressure that we can safely maintain and have a stable wellbore while we're drilling, and they're given by these limits here. Again, the assumptions here are that the horizontal stresses are equal for the shear failure limit, and we're neglecting the tensile strength of the rock in both cases. Okay, so these critical pressures now allow us to define something that in oil and gas drilling we call the mud window. And what the mud window represents is the range of drilling fluid densities that you have to stay between so that you don't cause tensile or shear failure, okay? And so the way that you get the mud window, and we'll do an example problem in just a minute, is that if you know the safe wellbore pressure at a specific depth, you can convert that to a pressure gradient. And that pressure gradient then maps directly onto a density if we assume that the pressure is hydrostatic in the wellbore. And so then we get that drilling fluid density, which is the same thing as a mud weight. That's what we call that. And then we see what the range is between those, and that's called the mud window. So let's do a mud window example here so you get the idea. So we talked about pressures and pressure gradients in the context of capillary seals in the previous unit on CO2 storage. Similar principles apply here when you're drilling. And so the idea here is that you've got a column of fluid within the wellbore, and everywhere within that wellbore, you've got some hydrostatic pressure that's due to the weight of the entire mud column above you. So in this situation, we're going to assume we've got a normal pore pressure gradient, so nothing fancy going on with the pore pressure. It's 0.433 psi per foot. We'll assume that the horizontal stress gradient is 0.6 psi per foot. So that means that as you go deeper within the earth, the horizontal stress increases at a rate of 0.6 psi. We're considering a depth of 3,000 feet below the surface. And so how do we get the safe pressures there, and what's the safe mud window? Okay, a couple of other items that we need. We've got an angle of internal friction for the rock. 30 degrees is a pretty typical value for a sandstone. We'll ignore cohesion. And so the question is, what's the mud window? Okay. Excuse me. Okay, so what we're going to do is we're going to figure out what the pressure in the wellbore is and what the horizontal stress and the pore pressure are at our target depth. So that was 3,000 feet. So we know that the pore pressure gradient is 0.433 psi per foot. So it's easy to get the pressure there. We just have 3,000 feet times 0.433, and that gives us 1,299, just under 1,300. That's PSI gauge. So we're not considering atmospheric pressure. That's fine. Similarly, the horizontal stress is going to be depth times gradient, and that gives us 1,800 PSI, and that should also be PSI gauge. Okay, so that's what the horizontal stress is. So now we can calculate the lower bound and the upper bound of the mud window in terms of pressure, okay, using those equations that we derived. Okay, so the lower bound is going to be given by that shear failure limit. So we can run through this equation. We know that the cohesion is 0, so that makes things easier. We know what everything else in here is. We know horizontal stress, we know angle of internal friction, and we know the pore pressure, which we just got. So if you plug in all those numbers, you get a minimum wellbore pressure of 1,550 psi. And again, that's PSI gauge. Okay. Now, similarly, we can get the upper bound. So this is our maximum pressure, and this is the tensile failure limit. Same thing, the horizontal stresses are equal to each other. And so we just plug and chug, and we get just over 2,300 psi. So that's the upper limit. Okay, so that's in terms of pressures. Now, what we really want is in terms of drilling fluid density. So the question here is, what is the density of the fluid that would give us this hydrostatic pressure at a depth of 3,000 feet? Okay, so we're kind of working backwards now. So there's a simple conversion that you can do, and it is you take your pressure and you can convert that into equivalent density in pounds per gallon by doing the following. You take your pressure in PSI and you divide it by the depth. That gives you an equivalent pressure gradient. Okay, so for example, for the lower limit here, if my lower pressure limit is 1,550 PSI, that is equivalent to a hydrostatic column of fluid with a pressure gradient of 1,550 divided by 3,000, whatever that is in PSI per foot. Okay. Then you take that ratio and you multiply it by 19.2. And that's the conversion factor that says what density of fluid would give me a pressure gradient of whatever that is. And so we end up with a lower mud limit, or excuse me, a lower limit to the mud window of 9.9 pounds per gallon. Okay, so again, if we have a static column of drilling fluid at 3,000 feet depth, the pressure in that mud would be 1,550 psi gauge. And so we can do a similar thing to the upper limit, and we end up with 14.7 pounds per gallon. So it's a little bit, there's a little bit of a couple of steps in there that you need to take to get from the pressures to the densities, but it's not too bad. You just have to follow the steps. And if you're drilling this well, now you know that you need to keep the mud weight between 9.9 and 14.7 pounds per gallon to be able to safely drill through those zones. Okay. Any questions about that example? Yeah. Okay, fantastic. Okay, well, that's the end of our unit on geothermal drilling. So we talked about deep drilling, we talked about shallow drilling, and everything in between. And we'll talk in the next little bit here about some newer technologies that are enabling us to drill even deeper. So, all right, so let's get to that. Oh yeah, just a heads up. I think we're going to, well, we'll see how much we get through on today, but there's gonna be another group project at the end of this unit. We're gonna be talking about doing research on induced seismicity associated with geothermal drilling, which is kind of a hot topic. And depending on how much we get through, my intention is probably to kick that off with a work session Friday, and then we'll start presentations a week from today. So just a heads up, I'll throw a Canvas announcement out about that as well, just so we're all on the same page. Okay, but yeah, high enthalpy systems and induced seismicity. Okay, so first of all, everything we've been talking about so far basically has been focused on using geothermal energy for heat exchange. And so this is either for domestic heating or cooling or district heating or cooling. But if you are drilling into really, really hot rocks, then you can actually produce steam, either dry steam or wet steam, and just run that directly through a turbine to generate electricity. And so there are certain circumstances where that may be more valuable than doing heat exchange. But it does require very special conditions. So let's go back to our temperature entropy diagram here. This is one for water. And so you can see there's a couple of regions that you want to pay attention to. So ideally, if you're doing high enthalpy geothermal, you're going to be producing nothing but steam. There's going to be no liquid water coming out. It's all going to be vapor. So you can see that, so here's our 1 atmosphere line, right? It's 0.1 MPa. You can see that that 1 atmosphere intersects the phase envelope somewhere around 120 degrees Celsius. So you want your fluid to be coming to the surface at 120 degrees C, okay? And depending on how deep your reservoir is, you have to account for heat loss between where how deep your well is and when that steam actually gets to the surface, okay? And the general rule of thumb is that you want your subsurface temperature to be greater than about 300 degrees Celsius. So here's 300 degrees C. If we come over here, 10 megapascals. In terms of hydrostatic pressure, that corresponds to about 1,000 meters depth. So if you're shallower than 1 kilometer or something, that's kind of your ballpark. You want to be at least 300 degrees C in the subsurface. And that will allow you to produce dry steam, which is going to be steam where you're over here completely in the vapor region. Now, if you're lower temperature than that, you'll be in the 2-phase region here. So you'll be producing some steam and some liquid water. It's called wet steam. And there are certain geothermal power plants that can get away with a certain amount of liquid water where you can separate it out and just extract the steam. But, you'd still want to be over here in the, higher vapor fraction part of that two-phase region. So, but that's your ballpark numbers. So 300 degrees C in the subsurface, and you want your steam to be at least 120 when it comes to the surface. Then you can run it through your power plant. So let's look at a map here. This is a map of global heat flow. Heat flow on the surface of the Earth varies considerably. This contour here is going from 40 to 120, and that's in milliwatts per square meter. The places you want to look for are going to be where you have very high heat flow, because that means you've got hot rocks very close to the surface. Okay. Now, it's a little hard to see the outlines of the continents on here, but those of you who have taken geology can probably recognize that most of the areas with high heat flow are in the middle of the ocean. These correspond to mid-ocean ridges where new crust is being generated. And as a consequence, the mantle is very close to, if not right at, the seafloor. So you've got very hot rocks, very shallow. There's a couple of places where that situation does actually occur on land. One of them is right up here. It's Iceland. That's where most of your high enthalpy geothermal is being done today. But the Western United States also has some regions where you've got hot rocks very close to the surface. And one of the better known geothermal facilities in the US is the Geysers, which is in Northern California. And that's a high enthalpy geothermal system where they generate electricity from steam coming out of those wells. We'll look at that in a little bit. There's also other areas where you can potentially have this work. It's basically going to be areas where you've got early stage continental rifting, so the crust has gotten very thin. Western North America is a good example of that. The area around the Red Sea in the Middle East is also an example where you've got thin crust and hot rocks near the surface. And then kind of other random places around. Okay. So the deal with high enthalpy geothermal is that it's very hot. Okay. I guess that's probably obvious, but that introduces a number of challenges, and a lot of it is related to materials. Okay, a lot of the stuff we use in conventional oil and gas drilling is rated maybe to 180 degrees Celsius. Okay, but if we're operating at upwards of 300 degrees Celsius, you need different materials, you need different drilling equipment. There's a lot of stuff that needs to be different, so you have to think carefully about it. Corrosion happens a lot more rapidly at those temperatures as well. So yeah, you have to think about that. Generally, when you complete a high enthalpy well, you're going to be producing the steam through things that kind of look like kitchen graters, box graters. They're called perforated liners. You pre-perforate them at the surface, and then you install them down hole, and the steam just comes in through those holes and comes to the surface. And you'll typically have a pretty large number of casing strings that get smaller and smaller as you move down. Remember what I said is that you want to maximize the energy flux at the surface while minimizing the heat loss along the way. And so depending on how hot the subsurface is and how fast the steam is coming out, you need to do these calculations about what the sizing of your wellbore has to be as the steam comes to the surface, right? Because one thing that, we think about this a little bit with oil and gas production engineering, particularly when you've got volatile oil that's going to start to vaporize as it comes to the surface. You have to think about how that fluid is going to expand as it comes to the surface. Now, that's a problem with oil and gas production, because when gas comes out of solution, you get this phenomenon called gas holdup, which is where the gas prevents the oil and the other fluids from coming out to the surface. So you need to be careful about that. With high enthalpy wells, the more the gas expands, the more heat it's going to lose. right? And so you want to balance the ability of that gas to expand with reducing the heat loss. So, this is a pretty dramatic example. You're going from a 6.5-inch liner down here to 27.5 inches at the surface, but you might not be able to get away with that. So anyway. Okay, the power generation is pretty straightforward, and it's actually, the systems are simple enough that I can actually draw them myself using built-in PowerPoint graphics like I've done here. So here's your steam well. Steam comes up here, goes directly into the turbine, runs the turbine, you generate your electricity, and then you send that to the grid. And then what you're left with, the waste product at the end of this, is basically hot water. And, it's still, obviously, it's liquid water. It's cool below the boiling point, but it still might be, 70, 80 degrees Celsius. So that still has useful heat that you can extract from it. I know that in Iceland, one of the things they do is they use the wastewater from their power plants to heat greenhouses. And so they'll often have greenhouses co-located with power plants, and they can grow produce and stuff like that. You can also use it for a district heating system or something like that. I promised I would talk about the geysers, and here is a photograph of the geysers. So this again is in Northern California, kind of north of the Napa region up there. And the geology there is kind of complicated, but they've got very hot rocks about 7,000 or 8,000 feet deep. And so they've been operating the geysers have been operational for quite a long time. I think going back maybe to the 1970s. I could be wrong about that. But anyway, yeah, it's about 300 degrees Celsius. And what they do with their wastewater is they just re-inject it. So the idea there is that they're kind of trying to use this almost as a closed loop system where they send the water back down to extract heat, and then it comes back. There's one problem. I'm getting a little bit ahead of myself, but there's one problem with doing this, which is that injecting cold, and I'm going to say quote unquote cold. So if you inject 60 or 80 degrees Celsius water into a 300 degrees Celsius reservoir, that is a substantial temperature difference. And you can cause this phenomenon called thermal shock, which is where you actually mechanically destabilize the rocks, because when you cool rocks down, they will contract, right? They get smaller in volume, and that can cause all kinds of adverse things in the subsurface. And so there's a significant, including induced seismicity if you reactivate faults. And so there's a big thermal management program that you need to have, that you make sure that you're not depleting the heat source and thermally shocking the rocks too much when you re-inject those colder fluids. So that's just something you have to be aware of. Okay, if you're generating wet steam, so maybe you're not quite at that 300 degrees Celsius range, but you're still getting out some steam and some hot water, you have to add a gas water separator before your turbine. So you send the gas, or the water vapor into the turbine, and then same thing. And then the hot water comes out the bottom of the gas water separator, and then you can do the same thing. So it just adds a little bit of complexity. Obviously, the efficiency goes down because you're not using all the energy that's coming out of the ground to generate electricity. You have to siphon some of it off. But this, again, is something that you can do. Here is a good illustration of a flash steam power plant. This is in Iceland. And there's a bunch of stuff in here, but the important things are, here's the actual well, so it's right there. And they've got a pipeline, and then there's additional gathering pipelines that come in here to the separator. And this is the separator where you're separating off the water from the gas. The gas comes in here to the turbine hull where it generates electricity. And then they've also got a heat exchanger here, which works with the hot water that's been siphoned off. So generally, whenever you see photographs of these power plants in Iceland, there's a lot of steam coming off of them, which which makes sense. But that's kind of typically what they look like and the scale of these things. I think it's, Iceland gets, I think, upwards of 99% of its electricity from geothermal. So they really take advantage of the resource that they have. Okay, so in Iceland, you can drill not very deep, I think less than 1 kilometer. You can get these really hot rocks. But we're not that lucky in most parts of the world. And so if you do want to generate utility scale electricity from geothermal, you might have to consider a technique called enhanced geothermal systems. And these are going to be situations where you have to drill down 5, 6, 7, 8 kilometers to get to the very hot rocks that you're interested in. Okay. I think in the interest of my voice, I'm going to stop there. We will reconvene on Monday and wrap up our discussion of enhanced geothermal and induced seismicity. So I hope to see you all then.